Hello, ladies and gentlemen, and welcome back. Root Beer here, still looking at our 2018 Canadian Open paper. We're looking in this video at question B3. If you haven't given it a try, here it is. Feel free to pause the video and take a gander at it, see what you can see. So we've got a new function. The doubling sum function is defined DAN. So there's n terms, and we're adding them up. It looks like you take the A you're given, then you double it, then you double that, then you double that. So we just keep multiplying by 2s. And this 530 is 5 plus 2 times 5 plus 2 times that. So 2 times 2 times 5. And this, you go till you have 3 terms, add them up, that's 35. And then what else have we got? Another example, D11.5, 11, double it, double it, double it, double it. So we'll double it 4 times in the end. And add them all up, and I'll take their word for it that it's 341. All right, determine the smallest positive integer n, such that for every integer between 1 and 6, there exists a positive integer ai, so that DAI is n. So n can be written as a double sum with the second number being 1, 2, 3, 4, 5, or 6. Okay. So all we need to do is we need to find this n there, but we should explain ourselves. All right, so let's investigate this function a little bit. Now there's something interesting that happens when you add up powers of 2. And that is what we're working with. And in order to make n terms, technically we've got 2 to the 0 here, and 2 to the 1, this is 2 to the 2, 2 to the 3. So if you start counting at 0, you'll get n terms, with the last term being 2 to the n minus 1 times a. Notice we multiplied by 2 4 times when we were doing D11.5. Okay? You can take out a factor of a here. You get 1 plus 2 plus 4, all the way up to 2 to the n minus 1. And if you haven't seen this before, if you add up your powers of 2, there's a very, very quick way to work this out. You can view this as a geometric sequence if you want, or geometric series because it's being added up, and that's one way to do it, but it's a fairly common result. That it turns out you just go to the next power of 2 and subtract 1, and that's the sum of all the previous powers of 2. Think about it for a moment. 1 plus 2 is 3, which is 4 minus 1. 1 plus 2 plus 4 is 7, which is 8 minus 1. So you can readily convince yourself that I am telling the truth. If you want to, commit that to memory, or you can look up geometric series and learn some formulas that work for that sort of thing. But it's a good thing to know. So no matter what DAN is, we've got our choice of A, we've got our choice of N, but it's going to be a multiple of a power of 2 minus 1. And what are we asked for? We're asked to find the smallest number that can be written as D something 1, D something 2, D something 3, D something 4, D something 5, and D something 6. Now the somethings can change. These AIs that they're asking about can change, but I can definitely say that I know the n values, the second values, 1, 2, 3. This is going to give me certain factors that n must have. I'm going to switch it to capital N just because they had a little n twice in the question. So if n is DA1, 1, then 2 to the 1 minus 1 divides n, which is not that interesting. That just means 1 divides n. Well, every number does that. But since it's got to be D something 2, then I can see 3 divides n. We can keep going for the rest of them. A5, 5, A4, 4, A3, 3, So 2 to the 3 minus 1 must divide n. Well, that's 7 divides n. and 2 to the 4 minus 1 divides n. So 15 needs to divide n. Now, what about these AIs? Just take your n and divide by the 2 to the something minus 1, and you'll have what has to be the first thing, the a. 2 to the 5 minus 1, so 31 needs to be a factor. That's kind of interesting because it's prime. 2 to the 6 minus 1, so 63 needs to divide n. So the smallest n can be is the lowest common multiple of all these things. So 1, 3, 7, 15, 31, and 63. So what is the lowest common multiple of those? Well, you don't really need the 1. Everything's a multiple of 1. But the way to do this, sort of the quick way to do this, is to look at prime factorization. So 3 is just 3 to the 1. 7 is just 7 to the 1. 15 is 3 to the 1, 5 to the 1. 31 is just 31 to the 1. And 63 is 9 times 7, so that's 3 to the 2 times 7 to the 1. So to create the lowest common multiple, you go to each prime and ask which is the highest value of that prime that is that appears as a factor anywhere. And that's actually a 31, not another 3. So we do that for 3. We'll need to have a 5, 5 to the 1. Couple 7s, but the highest power of 7 I see is 7 to the 1, so we don't have to worry about that. And then finally 31 to the 1. So this should be the smallest n. Lots of n's. Any multiple of this will work. And so we'll just grab our calculator. 3 squared is 9 times 5 times 7 times 31. Wait, actually, no. Yeah. I can't remember now. Are we allowed calculators for this paper? Oh, goodness me. Yeah, you're allowed calculators in the open. It doesn't say. And I can't remember off the top of my head. Okay, doesn't matter. I'll just work this out by hand. So 9 times 7 is 63 times 5. Well, let's do 31 times 5. 15. Times 63. 5, carry the 1, 6 to the 1, 4. And 0. 6 times 5 is 0. Carry the 3, 33. 9. So 5, 6, 7, 9. So the smallest n can be is 9765. I think I'm confusing this for some reason right now. It's completely escaping me, but I think I'm confusing this with the Manitoba contest, which I've also been recording recently, and that is no calculators allowed. But either way, I mean, we can do it by hand if we have to. All right, so that's the smallest possible n there is, and that's really all we have to say about B3. So up next, we're going to finish off part B of this contest with B4. I will see you for that in the next video.